All right, in this video, we're going to be doing the 2019 AIME number 1 problem number 1 and on from there. It says, consider the integer n equals 9 plus 99 plus all these 9s, and the last one's going to have 321 9s in order to express it. Find the sum of the digits of n. Again, when you're taking the test, you have 3 hours to answer 15 questions. That's 12 minutes per question on average. Granted, the early questions you're going to want to spend less time on, and the later questions more time on. But there really isn't that much of a time pressure that you're going to feel. Most students taking the test are not going to be answering all 15 questions anyway. So don't really worry about the time so much. Don't feel pressure. Just start thinking about different approaches that we could take. The first approach that you might consider is maybe you would say, well, let's just do patterns. What's 9 plus 99? And you would get 108. Okay, what's 999 plus 99 plus 9? And basically you're going to be adding 1,000 to this and then subtracting 1. So you'd be at 1107. And you could keep looking for patterns here. You know, you can already see some developing. There's a 0 in the second to last position, a 0 here also. So maybe there's something we could do with that. The number of 1s is increasing. We could analyze going that direction. But when we start thinking and looking for a pattern, basically, that we could extrapolate to the whole thing, but when we start doing that, I don't know, it feels a little bit like the end of that path is not going to be enjoyable. In fact, we might not find a pattern if we did this 4 or 5 more times. And I don't really want to do the iterations. The next one, adding, 10,000 minus 1 to this, and so on. I guess we could think of ways to make the process faster, but I kind of don't want to do it, right? And when you get that feeling of kind of not wanting to go a certain route, it's less true on the AIME than it is on the AMC, but it's often a sign of there's probably a faster way. And so what we want to do is now think about, because we have more time, it's okay to start a method, an approach, and then abandon that approach and try a different one. That's totally okay in problem solving. Get used to it, especially on the AMC and the AIME. And you have more time on the AIME, so what's to worry about? So what else can we do? The thing that I'm going to do next, it kind of comes with experience. If you've never seen it done, then you might think of it. I'm sure, obviously somebody thought of it at some point prior to us, so there's a chance that you'll stumble across it over a given amount of time. But if you've seen it done once, then this is the kind of thing where that experience lends to this problem. And I've seen something like this similar before, and one of the strategies or tactics that you can do is you can simply make this 10 minus 1 and make the next one 100 minus 1 and then 1,000 minus 1. And let's just stop here before we continue the process, and let's see what happens with just this. And we're going to again look for a pattern. Add all the tens parts up, 1,110, 1,110. How many 1s do I have? This is the kind of things, these little questions like this, that you need to be asking yourself to make powerful observations that you can then capitalize on to find a more efficient solution, right? So there's 3 1s. Well, there was 3 powers of 10 here as well, 10 to the first, second, and third. And then we're going to subtract 3. How many 1s are we subtracting? The same as the number of 1s in 1,110. So we should probably expect that maybe is something. In fact, let's go back an iteration. We could also go forward 1 and see what would happen if I just did these 2. I would get 110 minus 2. How many 1s did I subtract? The same as the number of 1s in this expression. And you can see that the next sum, this would be like sum number 2, if you will, and sum number 3, the next sum is probably going to have 4 1s, and I'm going to subtract 4. It's also always going to end in 0. Okay, then let's fast forward to the end. If I've got the last number, and also let's do something else, one more observation we want to make. The number of 1s was equal to the number of 0s in the final expression right here. Right, this is 10 to the third minus 1. You could also think of it as the exponent in that, right? And so this was the third number. It had 3 9s originally. It has 3 zeros here. So then if we have 321 9s, we would have 321 zeros in this part of the expression, right? It would be a 1 with 321 zeros, and then minus 1 would be the last number. But we don't really care about that. We actually want to get to the sums value, which we can see the sum for the third one had 3 1s and a 0. So the sum for this, the sum of 321, the first 321 terms, is going to equal 321 1s followed by a 0, and then minus all of the 1s that came on the end of those 321 expressions. So we'll now subtract that. We also want to start thinking about now, there's 321 1s here. We also want to start thinking about what the end game is going to look like now. Because we really don't want to write this all out and then subtract 321. Let's think about this. If I subtract this 3 from this number, it comes to 1,107. Are these first two ones impacted by the subtraction? No, they're not. They're not affected in any way, shape, or form. And that's what's going to lead us. Same thing here. These two, this one here will not be impacted by subtracting 2. I will get 108. So because we're subtracting 3 digits, only the last 4 digits of this number are going to be impacted. So the last 4 digits will be 0, 1, 1, 1, and then you're going to have how many more 1s going this way? Well, you had 321, and 3 of them are still there, so you're going to have 318 1s here in this part of it. And then you're going to have this 1,110 minus 321. And then I'm kind of lazy to do normal subtraction. You probably could, but I'm just going to add 679 to this to get myself to 1,000, and then add 110 to that to get the difference of 789. If you're not sure what we did, it's kind of a trick of subtraction. Instead of subtracting, you actually add to the bottom number until you get to the top, the first number, right? So by adding 679, it gives us 1,000 right there, and we have 110 more to go. We add it. Adding these two gives us 789. So that 789 is what this is going to end in, but because it's going to be 4 digits, we have to end in 4 digits. So it's going to end in 0789 after the subtraction is complete. Okay, then all we have to do now is add it all up. 318 ones is 318. It's the digit sum, right? The sum of the digits. And then you're going to add 15 plus 9 is 24 to get 342, and that's the answer. All right, and continuing on with the 2019 AIME number 1, problem number 2. Jen randomly chooses a number j from 1 to 20. Bella then randomly chooses, or Bela, a number b from 1 through 20 as well, but distinct from j. Okay? The value of b minus j, so Bella's number minus Jen's number, is at least 2. So we could say b minus j greater than or equal to 2. With the probability, we can pause and put a p around this. The probability that b minus j is greater than or equal to 2 can be expressed in a particular form. This is a standard ending, a fraction where the fraction values are relatively prime positive integers and you find their sum, or maybe their difference, or maybe one of them. It doesn't really matter what the ending is. As soon as it says probability that can be expressed, just find the probability and then go back and figure out if you've expressed it how they want you to and what they want you to do with the expression at the end, such as adding the values of the numerator and denominator. So, how can we think about this? Let's start off with, we could do it like a permutation. Because we're not going to have 2 of the same value because it's distinct from j, then we can think of it like, b's choice and then j's choice. And b could choose, it doesn't really matter that b's choosing second. It's still going to be that there's 20 choices for the first choice and 19 choices for the second. We could also think of it as the permutation of 20 things taken 2 at a time. You might see the different notation as 20p2. Those are the same thing. And you could calculate it with this as well, but it's going to come out to 20 times 19, which is going to give us 380. In probability, it's usually the denominator that's easier to find. That's because probability is the ratio of favorable outcomes over possible outcomes. And almost always, possible outcomes will be what's easier to find or found first. Okay, so next up, we just need to know the number of ways that this happens. Well, there's several approaches that we can take, and we are in fact going to take more than one. The first approach that we'll take is, I don't know, it's a little bit less mentally challenging, I suppose, to think in this manner, but it's effective and it gets the job done. So let's start with it, and then we'll try to confirm it with another method that might be slightly more efficient if we used it. Okay. So I basically need, let's just say that Bella gets a 20 somehow. If Bella gets 20, if that's her number, then Jen could be anything from 1 to 18. All of those values, 20 minus all of them, will be greater than or equal to 2. So there's 18 scenarios where this works. And if Bella gets a 19, Jen can have 1 to 17, and there's 17 scenarios where this works. We can see where this is going. It's not hard to extrapolate down to when Jen can only get a 1, Bella would have had to have a 3 for that to work. If Bella has a 3, Jen has to have a 1 and 1 only, is what I mean to say. So then this is going to give you one way, and you can imagine that everything in between is going to be filled in, and you simply have the sum of the numbers from 1 to 18. We call that situation the triangular numbers. That's because of various reasons. Look it up. It has a formula. The sum of the numbers from 1 to n is equal to n times n plus 1 over 2. Simply taking 18, which is the last number in our set, we can plug it in to get 18 times 19 over 2, and 2 goes into 18 9 times. Now, this over here, when I calculated this, it was so easy to calculate we did so, but it might have been better if we just left it as 9 times 19. And the reason is we need m and n to be relatively prime, no common factors. If we now wrote what 9 times 19 is, which is 171, that's 9 times 20, 180 minus 9, then you might not think about how it reduces, right? Or you might take a while to come up with how you reduce this. And there's kind of a principle in problem solving where you shouldn't really calculate things until you have to calculate them, because there's often some kind of a shortcut. And if I had just left it like this, that shortcut is obvious. The 19s cancel. You get 9 over 20, and it wants us to do m plus n, which would be 9 plus 20, or 29. But we talked earlier about a second way. Is there another way to feel more confident in our answer? Especially on the AIME, you don't have multiple choice to make you feel more confident, which can actually sometimes mean that you got tricked. But instead, you need to maybe take more time, the 12 minutes, or more minutes at least, more seconds, to kind of think of, is there another way I could have thought of this? Is there another reason why it might be 171? Let's think about it. If there's 380 outcomes, right, 380, then you would expect, and they can't have the same number, there's no ties allowed, that half the time Bella would have a number higher than Jen, and half the time Jen would have a number higher than Bella. We need Bella's number higher than Jen. That's going to be half of those 380, which is 190, right? And of these 190, how many fit this criteria, where the difference is more than 2? Since they again can't be the same number, we simply subtract all the cases where Bella minus Jen is equal to 1. That would mean Jen's number is 1 less than Bella's. Jen would have to have the numbers 1 to 19, of which there's 19 cases. So if Bella had 1, Jen would have to have the numbers 1 to 19. So if Jen had 1, Bella would have 2. If Jen had 2, Bella would have 3. All of those cases would give a difference of 1, which we don't want. We don't want a difference of 1. We want the difference to be 2 or more. So we simply subtract the 19 ways that you get a difference of 1. Indeed, that's 171. We've now done 2 methods, and they have confirmed each other. That feeling of confidence that your answer is correct is priceless. You should work to achieve it on as many problems as possible, because what it does is it enables you to think about the next question without the residue of the previous one haunting your thoughts. Because while you're trying to solve the next one, your mind's kind of thinking back to the previous one or a previous one. Did I really get that right? I don't know. You want to eliminate that feeling so you can give 100% of your focus to the next question. It won't always be possible to come up with 2 methods, but at least give it 30 seconds of thought before you move on to the next question. Okay, we'll go on. All right, in this one, we're going to do 2019 AIME 1, problem number 3. In triangle PQR, PR is 15, QR 20, and PQ 25. Pause and think about what you just read. Obviously, it's a 3, 4, 5 triangle. So you're simply going to create a triangle to start before you continue reading. Make it approximately a 3 to 4 ratio on the legs. Maybe it should have been a little longer here. I don't know. It doesn't really matter that much. 15 is one leg and 20 is the other. Since this is 15 and this is 20, the point common to both of these is R, so it will be the 90-degree angle here in the corner. PR is 15, QR is 20, and PQ is 25. All right, we got it. Points A and B lie on PQ. Now, something that I like to do on these kinds of questions where they start giving you additional points that lie on a side is, without putting the points on here, just kind of put them in the general vicinity so that you can move them onto the diagram when you know more information. But you also want to keep track of what's happening. It'll help you make sense of it. C and D lie on QR, so they'll be over here, and E and F are going to lie over here somewhere, with PA, that's from P to wherever A is, equal to Q to B. And we're going to skip down to the end of that sentence. It says it's equal to 5. Well, this is 25, so what else actually? Let's go to RD and RE and PF. So that's also 5. Then this is 15. I can split it into 3 equal pieces to get a better approximation of my picture. And we know that E and F are here. Once we've made that decision about what that looks like, we can put A at approximately an equal distance, and B approximately an equal distance here, and C here, and D here. It doesn't matter if you're 100%, accurate with the approximate lengths. Just get, fairly close so it's not a ridiculously off diagram. Okay, now what's going to happen? All of these things are 5, so that's 5, 5, 5, 5, 5, 5, and 5. And it wants us to find the area of hexagon ABCDEF, which you're just going to connect all of these points here. It's this inner part. Okay, again, we're not under time pressure. Just think this is a classic shaded region type problem. So in the shaded region problem, you find the area of the big picture and subtract the parts you don't want. Don't worry about right now if you're going to be able to figure out a method to get these 2. Perhaps this one's easier. Just start doing it, and then when you get to that point, see if your brain can generate the thought. So it's going to be 1/2 times 20 times 15. That's the base and the height of the big picture. And then we're going to subtract 1/2. We're going to do this one here because it's easier. Just get the low-hanging fruit first. You'll feel better and make it easier to get the rest. Now, how are we going to get this one? Okay, well, you have different options at your disposal. For this one, my first thought when I solved this problem is just to drop the altitude and create a similar triangle with the big triangle. And so there is another way. We'll get to it in a second. But this hypotenuse is 5 to a hypotenuse of 25. That's a 1 to 5 ratio. So the height drawn right here will be 1 to 5 with 20, and therefore that height is 4. 4 to 20 being 1 to 5. And we can quickly do base of 5, height of 4. So we'll have 5 times 4, and then we want to subtract 1/2 times this one. And this one, maybe I took a few more seconds to think about how you were going to get it. Maybe there's a similar triangle. And then it occurred to me the obvious, which you probably may have thought of by now or did yourself if you solved this problem before, and that's to approach it with the formula that the area of a triangle can equal half little a little b sine of c. The letters change, but the concept is the same. It's two sides and the sine of the included angle. And you might think, well, how are we going to get that? Because this angle's not a nice angle in a 3, 4, 5 triangle. But that's just it. We know the sine of Q because it's a right triangle in the big picture, and we can just use the sine of the big one to get it. The sine of Q in the big triangle. So our other two sides are the two 5s, right? So half times 5 times 5 times the sine of Q. I've called it C here, but that's just the generic formula that I use to memorize. To apply it, we need the sine of the included angle. And so sine is opposite 15 over hypotenuse 25. That's 3/5. All that's left to do is to calculate. The 5s cancel. You're going to get, maybe you could think about factoring out the half or something and saving. You're not going to save that much time. These calculations are too easy. Just get to them. Half of 20 is 10. 10 times 15 is 150. This is going to be 25 over 2. This is going to be half of 20, which is 10. And this is going to be 15 over 2 that you're subtracting. All right, 25 and 15 is 40 over 2. That's going to be 20. Subtracting 20 and 10 more is subtracting 30. 150 minus 30 is 120. See you in the next video.